Hello AP Chemistry students, hope you are enjoying the wealth of knowledge that Mr. Mauger has. He can definitely help you if you have any questions about the rest of these notes or on the worksheet or anything else, Mastering Chem, all that good stuff. So please take advantage of his knowledge, and he will be glad to help you. So I'm going to finish up the notes from the other day. Most of these notes are all repeat of what we did in honors chemistry, except for the very last page of notes. That is new stuff. So the off-ball principle, you can see the little diagram for off-ball on page 235, but it basically is showing you the order of filling electrons, and we always put electrons in their lowest energy levels first. However, that does start to go out of order once we get past the 3p sublevel. And on the next slide, we'll take a look at, well, in a couple slides, we'll take a look at the periodic table and its setup. Sorry about that. But after 3p, then we skip to 4s. So we do not do 3d, we do 4s. Then we do 3D. So the D's are always one energy level behind the S's. So we have 4S, then 3D, then keep going. We have 4P, and then 5S, and then 4D, then 5P, and then after 5P we go 6S, and then that's when the F's come in. So after 6S we see our first F, which is 4F. So the F's are two energy levels behind. And then we keep on going from there. And again, in a couple slides, the periodic table will show you this. And if you use the periodic table, that is the best way to do it, because the periodic table is set up to show you also the order of filling. So I recommend that as opposed to off-ball's diagram. So condensed electron configurations or shorthand notations, whatever you want to call them, usually that's what we write to save time. The other name for that is the noble gas notation, where we put the noble gas just before the element in brackets. That represents that both the noble gas and that particular element share the exact same electron notation, 1s2, 2s2, all the way up to where that noble gas is. And then all we have to do is write the remaining notation that comes after the noble gas to take us to that particular element. And so if we were to write the noble gas notation for calcium, let's see how this is going to go. This is where a I lost my thing. A stylus would really be helpful. And where's my arrow? Oh, there we are. Hello. Okay, couldn't see that. So if we have calcium, calcium has 20 electrons. So we would put the noble gas just before calcium, which is argon, in brackets. And so that tells us that both calcium and argon share the same electron notation of 1s2, 2s2, 2p6, all the way up through 18 electrons, which will end with 3p6. So then we pick up where argon leaves off with 4s, and then 2. So that gives us, oh my, I don't know why it does that. So the argon in brackets represents 1s2 all the way up to 3p6. So we don't have to write all of that now. We just put argon in brackets. But both calcium and argon share all that exact same information. Again, you don't have to write that. You just put argon in brackets, and then this is supposed to say 4s2. So it's also easier to count and make sure you have the right number of electrons. So argon has 18, and then 2 more in the 4s2 gives us calcium. Okay, let's undo that. Oh, no, okay, I don't know. All right, and what that noble gas notation also shows us is the core electrons. Those are the inner shell electrons. So if they're not valence electrons, they're core electrons. So all of those up here with that argon represents all those electrons, the 1s2 all the way up to the 3p6, those are its core electrons. The there we go. The valence electrons, those are our outermost electrons in the highest energy level, which can only be S and P. And so in the case of calcium, where'd my little pointer go? In the case of calcium, there we are. There you are. It has, these are its valence electrons, the 4s2 electrons. Those are its highest energy level. Now, the valence electrons can only be S and P sublevels, because again, as we said on the previous page, the D's, even though, like if we were doing, like right next to calcium scandium, if we did, oh, I lost my little marker again. If we were doing scandium's notation, here it is, that we would include a 3D1. That's supposed to say 3D1. But even though it's written out here and not included in the argon brackets, it's an energy level below 4s. So still only 4s2 would be the valence electrons. So scandium also only has 2 valence electrons. This 1 electron in the 3D sublevel is not considered to be valent. So that's why only S and P electrons are considered the valence electrons. And the reason why those are important, if I can, there we go, is that those are the electrons that are going to be involved in chemical reactions. So that's why the valence electrons are so important to know about, because they're the ones that are going to be making and breaking bonds in chemical reactions and forming new substances. So the periodic table, again, the way it's set up, the reason why it has the funky columns that it has is to show you the order of filling electrons. So the blue here, those represent the S sublevel, and each row represents an energy level. And so we start at the top, go top to bottom, left to right. So hydrogen is up at the very top left-hand corner, and so it is its electron notation with only the 1 electron is 1s1. And then helium technically could be written right next to hydrogen on the periodic table, and it is, with its 2 electrons, just 1s2. And then if we drop back down to the second row, then we start with 2s, and then if we fill both of those up, that becomes 2s2 like beryllium. And then jumping over to the far right hand, I got my laser working. Can't really see it too well, but over here, then these 6 columns over here, those represent the P's, and there's 6, remember P's can hold 6 electrons, so that's why there's 6 columns. First column would end in P1, then P2, P3, over to the noble gases, other than helium, which we already said helium ends in 1s2, neon, argon, krypton, xenon, radon, those all end in a P6. So just depending on what row they're in, they'll end in P6. Then we go back, so again we read the periodic table like a book, top to bottom, left to right. So then we go back over here, we have 3s2, then 3p, all the way through 3p6. Then in our 4th row, this is again where we go out of order like we were talking about before. Now we do 4s first, then all the transition metals, those end in D. So we have 3d all the way over to 10. There's 10 columns here, so we 3d10. Then we go to 4p, then 5s, 4D, and so on and so forth. Now, the only place that it really gets tricky, and honestly on the AP exam, they're not going to ask you anything with lanthanum or actinium. Let me get my little marker going again here. So here we have lanthanum, and here we have actinium. Some periodic tables put them down here. Lanthanum is a 5D1. That's supposed to say 5D1. And actinium is a 6D1. So just be careful with those. And different sources put them in different things, and that's probably why you really don't have to worry about these for AP. But just so you know, the lanthanum is a 5D1, actinium is a 6D1. But before we fill the rest of the Ds, then we fill the Fs. So after lanthanum, then comes 4F, which would be cerium, is 4F1. And we do all of the Fs. If you look at their atomic numbers, that ranges from 58 all the way up to 71. So this is element 71, which would be 4F14. And then after lanthanum, hafnium starts with number 72. So that's the intertransition metals come in between lanthanum and hafnium. So that's where the 4Fs. If you're doing a element that ends in 4F, you do have to include lanthanum, the 5D1, otherwise you'll be 1 electron short. Likewise for the 5Fs, we do actinium first as a 6D1 before we go on to thorium. It's not going to let me write down there, but thorium is then number 90, and that goes all the way through to number 103. So those are all 5Fs that come before Rutherfordium, which again, you're not going to have to do any of these. 104. Okay, so if you're doing any element between thorium and 103, you have to include actinium 61, otherwise you're going to be 1 electron short. Now if you're going all the way through the Fs and going to do an element up here in these Ds, or these 5Ds or 6Ds, then you don't have to separate lanthanum or actinium out. You can just do, after 6S, do 4F14, and then 5D whatever, or 7S2, 5F14, and then 6D whatever. So you only need to worry about lanthanum and actinium if you're going to stop in one of those F rows. And again, well, let's go on to the next slide. So again, that's what I was talking about, the lanthanides and actinides. Lanthanum number 57 comes before the first row of the intertransition metals, and actinium number 89 is a 61, comes before the second row of intertransition metals. But you only have to worry about that if you're doing one of those intertransition metals that's either in 4F or 5F. And there are a few anomaly electron configurations. Again, AP really doesn't ask you about this, so I wouldn't worry about this too much. We did talk about this in honors. So I call it the dwarf rule. If in the D or Fs, if you're one away from having a half full or full sublevel, we borrow an S electron, and that's what's going on here. Like with chromium would end where it's positioned normally as a D4, 3D4. Mother Nature doesn't like that, so it takes one of these S electrons and gives it to the 3D sublevel, so then we have 3D5, 4S1. So chromium would actually only be considered to have one valence electron. These are probably the only 4 that are, if AP ever asked you about this, they would probably only ask you about these 4. So again, don't worry too much about this rule. We did this a lot more in honors. But likewise, copper, that's one we talked about in honors. Copper's position on the periodic table would make it end in 3d9, but Mother Nature doesn't like being one electron away from a full sublevel, so it borrows one of these s electrons to make it 3d10, so then that becomes 4s1. So copper also technically only has one valence electron. And if you notice the way these electron notations are written, they put the D's in front of the S's. You can write them that way, but just remember the S's get filled first before the D's. But a lot of sources like to write them in terms of increasing energy levels. So they'll put the D's in front of the S's since the D's are a lower energy level. You can do it either way. So you can put 6s2, 5d, well really it'd be 5d10, or the 5d10, 6s2, either way. Okay, so if we were to, let's just pick one. Let's do tungsten. Tungsten's a good one. Where'd my little marker go? Where are you? Oh, there you are. Okay, so if we do tungsten right here, I'll do it up here so there's more room. And I'm doing this left-handed, so that's another reason why it's so messy. So tungsten is number 74. So we'll use the condensed electron notation. That will make it a lot easier. So that means we would put xenon in brackets, which represents the first 54 elements, saying that xenon and tungsten both share the same electron notation from 1s2 all the way up to 5p6. So then we pick up where xenon leaves off, which would be 6s2. Now, tungsten's number 74. So after 6s2, we have lanthanum, but we're going to come back to the D's anyway, so we don't need to separate out lanthanum in this case. We can just skip that and come back to it. We can go right to 4f14 for all of that first row of the inner transition metals, because again, tungsten is number 74. So all of these 4Fs come before tungsten, and then we can include lanthanum with the other 5 Ds. We don't have to, again, separate that out since we're coming back to the Ds. And based on tungsten's position, that would be 5D4. Now again, as we talked about up here, Mother Nature doesn't like a D4, so we're going to borrow one of these S electrons and make that a 5D5. And again, don't worry too much about this. AP really doesn't ask you much about that. Okay, so now on to the new stuff. This is stuff we have not done, and AP is really big on this. You will see a lot of stuff on this, and we'll do this a lot too. You have a whole extra practice worksheet to do today for what we call PES, or photoelectron spectroscopy. It's its own AP topic, but it's actually really easy. It sounds pretty tough, but it's very easy once you get the hang of it. So it's just a way of, there's a machine that can print out data like this. Oh, where'd my thingy go? Let me use my laser again. So there's a machine that can print out data that looks like this, and from this data we can figure out the electron structure of a substance. Oh crap, where am I? There we go. All right, here we go. So it creates a graph that shows the count of electron, as well as what it says down here, its binding energy. We'll talk more about that later on. You really don't need to worry about that. But what that does show is along the x-axis, the binding energy is increasing. Sometimes they can flip-flop that, so just be careful, but usually it's an increasing, meaning it's getting harder. It's harder and harder to remove. So the higher the binding energy, the closer it is to the nucleus. Okay, so and next chapter, in chapter 7, we'll talk more about effective nuclear charge and what all that means. But basically, like I was saying just a second ago, the higher the binding energy, the closer it is to the nucleus. So that's really all you have to worry about right now. And the peaks, these little peaks here, here, and here, those correspond to electrons in different sublevels. And the higher the peak, the more electrons there are in those sublevels. So that's why it says relative number of electrons. So if we had a really tall peak, there would be more electrons in it. Oops, crap, sorry. So the lowest energy peaks, those represent our valence electrons. So right here, the binding energy is very low. That's because there are valence electrons. They're farthest from the nucleus, so they can, basically what it does is they can be removed with much less energy. And again, we'll talk more about that in our next chapter. But the lowest energy, binding energy electrons, those correspond to our valence electrons. And again, as we move towards the core and the innermost electrons, the binding energy gets higher and higher. So the height, again, of the peak corresponds to the number of electrons in that particular sublevel. And so if we look at this, we can figure out what element this is. So we have 2 electrons here. And we really, well, obviously it's lithium because we only have 3 electrons, but besides just counting the electrons, we can see what their electron notation is. So we have 2 electrons here, and that's our highest, in this case, this is our highest binding energy, so that means they're closest to the nucleus. So that corresponds to 1s2. So those are our 1s2 electrons because they're closest to the nucleus. And then lithium's 3rd electron is farther away from the nucleus. This corresponds to 2s. And then we have 1. So since the 2nd energy level is farther away from the nucleus, it has a lower binding energy. So that's how we know that this is 2s. And over here, this has a higher binding energy. So this is the one that the energy level that's closest to the nucleus. So the highest energy level, the energy level closest to the nucleus will always have the highest binding energy. So again, just pay attention to the direction of the x-axis, and the ones that are higher and higher energy are the ones that are closest to the nucleus. The lowest energy ones have lower binding energy. So that's lithium's electron notation, 1s2, 2s1. That's what these peaks correspond to. Sometimes they'll give you the numbers right over top. Other times they might give them to you out to the side. So this would be 1, 2, and then if it had 6, you'd have a peak way up here at the top. So if this was a different element, it might have a big peak like that, and that would represent 6 or however many electrons. So the height of the peak tells us how many electrons. Its location tells us how close it is to the nucleus. And we just go in the same order, 1s2, 2s2, 2p6, so on and so forth. So finish up the homework sheet I gave you yesterday. And if you get that finished and want to turn it in today, that's great. If not, you don't have to. But then you also have a practice worksheet of this stuff, of PES. So make sure you pick that up. That'll be due tomorrow as well. So pick that up, and you can either be working on this. You also have Mastering Chem, pre-lab, post-lab. So there's all sorts of things you can be working on. And again, Mr. Mauger, I know, will be happy to help you. So have a good day, and I will see you tomorrow.